Good morning, good afternoon. Thanks everybody for joining. This is episode 3 of the BrightTALK series, Ask the Expert. Today we'll be covering machine learning and deep learning with David Talby, CTO of Pacific AI. David, do you want to say hi?
Hello everyone, glad to be here.
Awesome. So first off, I'll just introduce myself as a moderator. I've been at BrightTALK as a content manager for over 3 years, specializing in the BI and AI community. If you want to hashtag this series on Twitter, feel free to do that with hashtag AskTheExpert, and my Twitter handle is there as well. I encourage you to get involved on BrightTALK and on Twitter. Our Twitter handles are there, but please do submit the questions if you're on BrightTALK in the Ask a Questions box on BrightTALK, and we will be addressing those throughout. And if you want to check out the attachments, you'll see an upcoming episode for Ask the Experts, and I encourage you to sign up for that. So I will pass it off to David if you want to just kind of introduce yourself and talk about your background a little bit.
Sure thing. So my name is David Talby. My background is computer science. I have a PhD in computer science and an MBA. I've been building software for about 20 years now. And about 9 years ago, I really started working hands-on in machine learning. First, when I was at Microsoft, at Bing, so did some work on just classification problems, building data quality pipelines, and building obviously search and ranking systems. Afterwards, I spent about 5 years at a startup company called Datigio, which was focused on the healthcare space. Did a lot of work on natural language understanding, a lot of work on machine learning, and also some work on anomaly detection and data mining. And about a year and a half ago, I've started Pacific AI, whose goal is really to help companies build and implement AI systems. And really, this gives me now the very lucky opportunity to work with a large number of companies and projects and see really what people are doing in the data science and big data space to actually make AI a reality.
Awesome. Yeah, AI is picking up. It's an exciting time. And so could you real quick kind of give an overview of machine learning and deep learning for the audience?
Sure. So this slide, I found it online. There are probably even bigger and more impressive ones. And this really just goes to show that machine learning is way beyond the technical proof phase and well beyond probably even the hype phase. It's everywhere, and there are, at the very least, hundreds of companies who are using machine learning to make money and make their customers successful in everything. And machine learning at this point, I mean, it impacts who we meet, what we read, what we watch, how we eat, how we exercise, what access to money we have, where we travel, and at the personal level, and then at the business level, really most financial transactions, and most finance in a sense is done automatically today. A lot of marketing and advertising is done automatically today, and there are really whole systems of infrastructure within the economy that are deploying this in production. At the core technical level, machine learning system is really every system that basically that learns as it goes. So if you think about just from an algorithmic perspective, if I build a calculator, so calculator is not machine learning software because it does the same thing. So if I have a calculator, so I build a nice calculator app, a year later or 5 years later, it's still as good. It does the same thing and it works. If I build a spam detection algorithm or a recommender system for retail or a cybersecurity bot detection software, it needs to learn. Meaning my expectation is once I put the system in production that the following month and the following year it's better. And if it's not better, it's at least different. Because the system gets feedback from the environment, actually learns, right, without the programmer necessarily writing new lines of code. So that's generally what machine learning is, and obviously there are hundreds and thousands of algorithms and techniques around that.
Awesome. And can you just quickly overview how deep learning is different than machine learning?
Sure. So deep learning is also a generic term, but basically it's a subset of the algorithms you can use for machine learning, right? Or in general for software that learns as you use it. Is software that does this by using a neural network, and with deep learning specifically, we are looking at neural networks that have multiple layers, right? So they're considered to be deep in terms of the number of layers they have. And neural networks in general, and deep learning in particular, was a niche field of of AI and machine learning, computer science in general, until really 2012, when deep learning system really started outperforming state-of-the-art systems, mostly around computer vision, image recognition, and image identification. Since then, deep learning has proved to be invaluable and really providing state-of-the-art in really many image recognition, video recognition, speech recognition, natural language understanding, handwriting recognition tasks. The slide that you have here is, I mean, that's something that I recommend people to look at more. IEEE Spectrum has decided, has built this infographic. It basically keeps scores of the AI versus doctors debate. And what they're doing, they're, every other month or so, they survey new academic research, because, really every other week there's a new paper that says, in this specific area, we now have software that can outperform or equally perform as well as train doctors in a given specialty. So one reason I like this infographic is because, for me, I mean, it's a huge wave of optimism. Because really, if you just look at it from the perspective of healthcare and progress just in the science of medicine, there's so much that's been achieved, and it's still at the research stage, just in the past 18 months. That definitely makes me happy, and there are areas around mental health, around automated surgery, around really being able to read images, where we at least at the research level, we've been able to improve the state of the art in terms of how accurately we can diagnose, how accurately we can propose a treatment. That's one thing. The other thing that you achieve by having software that does this, potentially once you productize this, you make this much more readily accessible, because most of the population of the world does not have access to trained specialists. And if you look at those papers, and if you look at this infographic, basically all of the papers that are mentioned here are deep learning papers, right? So if you look at the actual techniques they're actually using deep neural networks in the underlying technique. And that's really, I think, one of the nicest proof points that, yes, look, this is a set of things that, is not just a nice algorithmic tree. I mean, it's actually delivering on a very wide range of commercially interesting and just society interesting problems.
Yeah, I think it's very interesting that healthcare is one of the leading industries adopting deep learning. So,
definitely.
So I want to just remind the audience real quick, feel free to ask questions in the questions box, and we will toss them up to David to answer throughout. But to start off, we have a couple prepared. David, so what do you think, why are data scientists considered not productive today, and how does one get solutions to production and have time to operate on them?
Yep. So that's I think one of the most common questions I hear today, mostly from CEOs. Where what people say is it's not that data scientists are not productive; it's that they're very busy. But what people are saying is, look, I hired a small data science team. We bought tools for them. We gave them the data. We invested, and like they're absolutely working, and they're building models, and they're doing other things, and some things are extremely interesting and exciting. But like nothing is getting to production. Okay, so either we're building models and then we don't quite know how to do what to do with them, or so we don't know how to actually get to a point where we're launching this and making money of this, and it looks like we are missing some pieces. And it seems that many teams are just have a hard time actually getting through the hump and getting to a point where instead of just having a data science team, you have just a team that actually delivers products and services for the business that happens to use those technologies. And I think underline, I mean, there are two kinds of problems there. One is that people treat data science and AI the same way they treat software engineering. And basically what they come and say, okay, this is within my engineering or R&D department. Should you be able to just use the same tools and the same processes? Okay, so I use Agile, so I use Scrum or Kanban or related technique. I use the same tools. People, when they spend their time, they write code, they test stuff. So I expect to have the same kind of project planning, the same kind of release cycle, the same kind of tools that are used, which is really not the case. In data science, first of all, it's much more around experimentation and repeated experimentation. The other thing that's massively different with AI is that a lot of the work really starts once you're in production, because once you start to actually get feedback, you need to be able to start retraining the system and improving it. Otherwise, it degrades very, very quickly. And many people just don't have either the processes or the tools to understand that's needed. The other thing that happens very often is that people have the data science piece of the tool set done, but not the other parts of the puzzle. So very often you need the team to do data labeling or data curation. You definitely need some kind of just software infrastructure and platform where you can train model, you can measure model, you can publish models to production as APIs, you can version them. You can have some kind of a continuous integration, continuous deployment tool set for models. And then there are concerns on security and how you actually collect feedback. And sometimes there are problems because data scientists really do not have the software engineering skill set, and software engineers do not have the data science skill set, and DevOps assume they can use the same tools, but really there are new tools that need to be built. And really because the industry is so new, there are many cases today where, really what companies do is they just go, head in and try to figure it out as they go along, which simply just takes a long amount of time. But I think what I would recommend to people is really, when you start, instead of coming and say, okay, let's tackle this data science problem, really should be around, okay, let's build a plan for going to production, see all the pieces we need. And very often you'll find out that the actual data science work can be, maybe 20-30% of the work that's actually required there.
Yeah, I find that interesting. Do you think that the engineers, cleaning and prepping the data, that should be separate from the data science role, and data scientists should purely be working in the production and analysis phase?
I would say usually yes. Usually a lot of the data preparation work, yes, it's a data engineering task or data curation task. And other people can do it. I've seen many cases where people hire, very highly paid, high-end data scientists, and basically use them to write scripts to clean up text files, because that's the blocker, and that's the work that needs to be done, and that's the majority of the work. So that's definitely part of it, and you want those people working in the same team. The only caveat I would put is that at the end of the day, data scientists do need to be, in a sense, very intimate with the data. So they need to really understand the data, what each field means, what are distributions, what are the gaps, where is the bias, what anything actually means. So in a sense, you do want them involved, at least in looking at the raw data and seeing what's there before it gets cleaned, because often they need to guide that process.
Got it. All right, so let's go on to the next question.
Sure.
So
go ahead.
Go ahead. Yeah.
So if I look at this question, this is a question I think I get almost every time, where someone either does something or they set up a team, and they realize all of the different pieces that need to be built. So they need to get labeled data, and they need to get a modeling platform, and they need to actually build their data science models, and they need to put them in production, they need to put some measurement or retrain pipeline, and they need to be able to scale it, and they need to be able to secure it. And there are a lot of moving pieces here. And then really the question is, okay, first of all, what can I even get? So what do I need to build versus buy? And buy usually means, first people start with open source. And then which kind of tools should I bet on? Because even if you look at deep learning libraries today, there are probably at least seven or eight that that can probably do the job and are viable. And really the main risk is first of all technically they're different, but on top of it, in 2-3 years probably not all of them would actually survive. And you don't want to bet on technology that basically will not have a community or will not be around during that time. So that's so definitely part of the challenge is really just knowing what to choose and how to build it. And I would definitely advise that if you're starting a project, at least you want to talk to other people who have been there and who have done it, so that you're starting with some reference architecture that's end-to-end and actually does what you need it to do. Otherwise, you can easily spend a couple of years just iterating and trying to understand how that works. The other question really is really what IP is valuable. So what's happening really is that algorithms are becoming a commodity, right? So if you really want to build a deep neural network or an image recognizer, honestly, I mean you can do it in 30 minutes using a bunch of open tutorials and software packages and sample data sets you can find online. There are many classes and blogs and webinars that show you how to do this. So usually the algorithms themselves, in a sense, it's almost like definitely not valuable to build your own. On the platforms, it's general also. Like owning your own platform is not something generally you want to do. So for the same way, you don't want your custom, you don't want your custom web server or your custom database or your custom, front-end JavaScript framework. You just want to find something that's good, has a strong community, and is evolving. What you do want to keep yours are first and foremost your own models. So if you actually build a predictive model that can can automatically understand X-rays, or understand emotion from speech, right, or recommend products for a certain category, then the models are definitely IP that you want to build and own yourself, and you will need to keep evolving it. The other thing that's very valuable to have is your own data. So if you have access to proprietary data, or you've built your own label data or curated data, that's another thing that definitely you want to build. And really, these are the two things I would focus on. Make sure you own your own models, you own your own data, and anything else really becomes open source and commoditized very quickly.
Do you find in some of those examples you gave as a pro to building it yourself, that directly combats like a top risk of relying on a third-party vendor? Or in other words, what do you think are some of the top risks if you do need to rely on a third-party vendor?
So say, look, there are two risks. There's the risk that you always have, in the same way that you take a risk when you rely on a database vendor or any kind of other software service or software library that you buy or you license. First of all, you need to see that they'll actually be there. And right now, this industry is this is an early stage industry. There are many players who are selling selling tools and selling libraries into companies that are building AI. So you want to make sure that either you really take in bet on something that you're comfortable will be there in a while, knowing that really the industry is still materializing. Right, so buying an AI tool today is a lot like buying a database management tool in 1980, right, where the whole database industry is still discovering itself. So either you can take the dependency, or you get into a position where you come and say you don't have a real dependency on the company because either it's open source or you get the full source code with it, or you have perpetual license. But basically, ideally, you get the source code with it, so you have the you have the ability to continue on your own if anything happens. The other thing to consider is really just the cost factor, because there it's since SaaS has become very, very popular, there are a lot of tools today that are priced by transaction, by user, or by server, and on an ongoing basis. Very often the pricing is very appealing at the beginning, but then it becomes actually prohibitive to scale. And also, as you scale, you may actually have a conflict of interest with your vendor, with your tool vendor. So that's another thing you want to consider in advance, another risk.
Awesome. So we got a couple questions. I want to toss one up from the audience right now. They were wondering, what is the typical or average time frame for classical statistical model development versus deep learning models from training to validation, and what have you seen in the verticals you've worked in?
Sure. So first thing what I would say, from my experience, it actually takes just about the same amount of time to develop, a good old, regression model versus a, very sophisticated deep learning model. In terms of the time it takes to build a model from data, to validate it, and to actually launch it. And that's because really most of the work is it's around data preparation. It's around really understanding the problem, selecting the right metrics to optimize, and then repeatedly experimenting and tweaking until you have a good result. And really what's happened today is that there are really several really good machine learning and deep learning libraries. So it's not like you have to go and re-implement an LSTM network, and then today you even have decent visualization debugging tools for deep learning network. So it's not about it's not as if you need to deeply understand or re-implement those algorithms. A lot of it is really the classical data preparation, understand the data, understand the problem, understand the goal, and experiment and iterate just with a different set of algorithms. Usually within a few weeks, you can get to a baseline model that works fairly well, meaning you feed the data, you tune the model, you tune hyperparameters, you select the features, you have a good baseline that's usually good enough for a V1. So usually, I would usually give it a few weeks to have a first working version for a new model, assuming you have enough data, right? And that's really the big if. So the big if, okay, do you have enough data to begin with? Once you have that V1, then really the question is, okay, once you start, once you put the thing in production, you start getting feedback. You should assume some operational work to actually keep improving the model or keeping it up to date.
Great. And I think I realized that we skipped a question, so on our slides here. So, yep. So in I guess in this early stage field, what do you consider, or what should people consider the state of the art for solving the problem, and how fast should or can they get there?
Yep. Yes. So obviously this question depends on the specific problem you're trying to solve. But I would say this is a question that I get pretty much on every project. Because what happens is, if people today want to build, if they want to build a mobile app, or if they want to build a web application or an e-commerce store, it's something that's been done hundreds of thousands of times before. So basically, people know or have a good gut estimate of how long it should take, what the process should be, what the cost should be. When people get to AI solutions, so let's say someone comes and says, okay, I want to build a new application that automatically reads chest X-rays and identifies if there's a potential risk of lung cancer or pneumonia, right? Or I want to be able to look at people's faces and look for signs for depression, or match potential people for dating, or anything of the sort. So first of all, because people have not done this, most people have not done this before. So the question, okay, how long should it be? Like, is it going to be days or weeks or months until I have something, and what is that something? And then the second question is, okay, what should I expect? right? Is it going to be 90% accurate or 50% accurate, or what are really the how would it look like? So in a sense, I mean, it's fun to work in this kind of environment where we really you need to it's that new. You need to explain to people even what they should expect. In general, usually what I do, I start with academic literature because really a lot of my work is looking at state-of-the-art academic research and really productizing it, right? So making writing it in a point where it's it's proper software engineering, it's scalable, it's robust, it's more resilient to errors in the data, far faster, monitored, secure. But then if someone says, okay, I want to be able to take pictures of plants and see if the plant is sick or not and classify what kind of disease the plant has, really you'd want to start with kind of say, okay, what have others been able to do, either in this space or similar spaces like skin diseases or whatever. And then usually per project we can tell people, okay, within a few weeks, here's the baseline we think we should be able to reach. And usually this is part of the sort of the research investigation we do. So what I would recommend that people do is really just really start with academic research because at least it would give you a baseline on what's achievable, right? What's been achieved. I would definitely not advise you to assume that you can put a couple of smart people to work for a few months and they'll outdo the entire academic community within a few months. That usually does not happen. Although obviously it might. The other thing to consider will have a huge impact is what kind of data you have access to. Okay, so for example, let's say that you want to take pictures of plants and see if what kind of disease the plant has. If you have a million images that were tagged by people who are specialists in this field, that you're going to get fantastic results. If you get 0, if you have 200, then probably your first project will be to actually collect the data, right, before you put any data scientist to work. So that's the second thing will have a huge impact on how long things will take and what you should expect to see in terms of accuracy.
Great. And just as a follow-up, within, I guess, I would assume within different industries, how you measure success would change, especially, in the healthcare industry that you have a background in. Success is more detrimental, or the lack of success. But do you see machine learning or deep learning implementations in other industries where success can be or quick success can be overlooked for the idea of implementing new technology and practices?
Yeah, so first of all, what I would say is a general practice if you're implementing any machine learning or deep learning solution, selecting the right metrics for success and the right metric you're optimizing is one of the biggest decisions you'll make when you design your project. In a sense, if you screw that up, you're pretty much guaranteed to screw up the project. And it's and definitely I would say it's domain specific and it's all problem specific. Right. So for example, if I'm, let's say I'm recommending, related products within an e-commerce application, I'm building a recommending system, right? Or I'm optimizing, the Netflix algorithms of why I should watch next. Then those two problems have different methods, right? Because in an e-commerce setting, really what I'm optimizing for is, how much people spend on the site, right? So I'm optimizing for revenue, or, if I'm smarter, I'm even optimizing for profit, right? Not just revenue. Right, so I want things that people will like and buy, but I also want to optimize how much profit I will actually make off the things that I recommend. If I'm looking at Netflix, probably what I want to optimize really is how long they actually stay and watch stuff. Right, so it's the time on site. Okay, and if you look at those two examples, really none of them are actually machine learning metrics. Right, so one mistake that people often make is they come and say, okay, I'm going to optimize precision recall, or I'm going to optimize the area under the curve. Well, in reality, you may have a model that has a better precision recall, but it actually causes people to buy less from you, or to buy less profitable items. Okay, which is in a sense is not the right thing to optimize. So really, what you want is we want to start really, okay, what's the business metric that I really want to move here? And make sure that everything you do actually looks at that one, right? So I would say, look, in most vertical is actually easier than healthcare because you have faster feedback. So anything that you do online, e-commerce, online advertising, real-time ad bidding, even cyber, in sense you get immediate, you get that kind of immediate feedback. So if I put a new recommender on the website and it doesn't work, meaning people buy less, I will see it within 2, 4, or 6 hours. I don't need to wait 2 years, right? Which sometimes you need to do with healthcare because to take 2 years to have this many lung cancer patients to actually go through the new process. If you're doing auto trading, right? Usually, sometimes within a few hours or a few days, you're going to see if a new strategy is actually slightly better or slightly worse. Also, assuming you have the right metrics in place in terms of risk and volatility and such. So I guess the main advice would be really just make sure you start with the right metric and never assume that somebody else's metrics is the right one for your problem because it's not a technical question. It's very often a business question first.
Got it. And so let's move on to skip this one that we already did. So I wanted to ask you, it's a big question today, but how do you deal with trust, bias, and explainability in AI, machine learning, and deep learning?
Yep. Yeah, so it is a big question. I would say that most people who ask it mostly want to make sure they're not going to get into trouble. So it's more like, I don't understand this whole bias thing or explainability thing, but like, can you build me a system that will not get me, in the news in a bad way? And I think it reflects sort of where we are as an industry, which is we are very, very early on in even understanding what the requirements are here. And here's beyond that what I'm saying. So explainability is basically also, it's not a technical question. It's a human-computer interaction question. Okay, which is when I tell you something, right? How do I explain the results for you? And explain the results does not mean that you need to necessarily be able to backtrack the entire algorithm. Okay, so one good example for this, we have the legal system. Okay, and when two parties go in front of a judge and they argue the case, the judge has a decision, and then he or she needs to explain the decision, okay, in detail. But explain the decision usually does not mean that they go, step by step, come and say, look, here's exactly how I went through, which means that basically every other competent judge should be able to arrive at the exact same conclusion, right? First of all, because different judges do arrive to different conclusions based on the same facts, right? And second, because look, when I read your explanation, I don't really want the whole reasoning. Okay, I want and it's really, what does the judge think that is most pertinent, is most important for me to learn, right? And the same thing, if I read a movie review, okay, I'm not interested in the full 2.5-hour experience. I'm interested in a 1-paragraph summary of, okay, look, here's what you need to know. So the way I look at explainability is less about the technical question of okay, can you retrace everything and make sure we have with this kind of full discoverability? It's more about can you make people comfortable that the algorithm here did the right thing? Okay, so for example, in healthcare, it's an absolute requirement. Okay, because let's say that I'm recommending that a doctor or a nurse actually change their behavior, right? So actually change the dosage or go and check up with someone or change the treatment or do something else. Okay, no competent clinician would change my dosage because the computer told them to. Okay, and no doctor would go to a patient and say, look, I think you should get 20 milligrams, but I'm going to give you 80 because that's what there was a pop-up that told me to do it, right? This will never happen. Okay, therefore, really, you have the question of how you convince the doctor or the nurse this is the right thing to do. Okay, and the way you do it is you do not show the entire decision tree and the entire logical explanation. The question is, okay, what's just from an interface design and user interaction perspective, what's the right thing to do? So that you tell them really in one sentence for the few seconds they have to look at this. Oh, okay, look, there's this fact and it's really important here and therefore we recommend this. and and actually get the behavior to change. So healthcare, or in general, I mean, if you look at education, even if you look at gaming, where you want to convince people to do something, explainability is very important. If you're looking at things like auto trading in financial systems, explainability in a sense is far less important. Because if black box A that makes me more money than black box B, then so plug it in, and that's how people mostly react to it in things not like just financial system, also things like real-time ad bidding and other this kinds of highly automated systems, even cyber, different kinds of automated detection and prevention programs work the same way. If it's better, that's all I need to know. And then really your explainability is the metric you're optimizing. Trust is, is an even bigger question, because trust also, it goes way beyond the technical problem, right? So it's really a lot of it, do I trust the product? Do I trust the brand? Do I trust your marketing? Do you make me comfortable? Is your system resilient? Does it not surprise me? From a technical perspective, when you get to it, sometimes trust means that you do not necessarily go for the highest accuracy because you want to have some stability within the system. So for example, when you work on search engines, you may want to actually retrain your ranking systems, even on the daily basis, right? Because you have feedback and you can change your ranking on one hand. On the other hand, people sort of assume that if I go into Google and I type something, I should see the same results day in, day out. And if I type in the same queries, and also because a lot of people really, you just use it for navigation, and I see different things, and it's just not stable. It reduces trust. Okay, and definitely if I'm making financial recommendations or product recommendations, right, or health-related recommendations, people don't want a system that changes its mind on essentially on the same data every other day. So the trust issues there. But the way I look at many of those problems, it's mostly an issue of really human-computer interaction more than anything. And I think the right way to think about it is really think about your product, think about the user experience you want to provide, and think about really, and then technically you can backtrack to what you need to make that happen. There are definitely algorithms like Climb for explainability. There's a set of, there are many ways for machine learning, deep learning algorithms to show what to show their work. I would say it's not technically correct that machine learning or deep learning algorithms are black boxes. I mean, it is just not. It is factually not the case. But usually when that comes the requirement, usually it means okay, understanding what the user interaction is, what the product needs to do, and then you can backtrack and sort of choose the right technical solution on how to really how to explain what happened and how to build that trust.
Excellent. And I was going to ask, what are some, after you have these algorithms in place, what are some best practices for identifying monitoring, whether it is you need to mitigate bias or you need to ensure explainability? What are some best practices post-launch?
Yeah, so say, look, the most important thing that people need to know about machine learning system post-launch is that once you put the system in production, its performance starts degrading. Okay, so in a sense, the day you put the software in production is probably the day you're going to have the best accuracy. If you do nothing, and then it goes south from there. And what you need to know, you need to be able. And if you really have a production system, which you need to succeed, you need to monitor your accuracy in production. Okay, meaning, let's say I'm actually recommending products for people. I want to see how many people are actually clicking on the products, how many people are actually buying them. If I'm going to stay with the same recommender, I'll probably see that number degrading over time, unless I have a team or a system that actually keeps updating it. So say one best practice is really just have that measurement in place. Most people just don't, but and it's almost ridiculous because if you think about it, no one will put a system in production without monitoring the servers. So knowing that I have enough CPU, I have enough disk space, I have enough memory, but people still put machine learning system in production really the same way they deploy software because they assume that it's software, it just works. Right? Like, I don't need to keep testing it in production. AI system, you absolutely need to keep testing in production. So first of all, just do the measurements. The other thing, if if there are concerns around a bias, make sure you measure on different sections of the population, because in a sense, all learning systems have some kind of bias. So if I build an algorithm tries to differentiate pictures of cats versus pictures of dogs, okay, so the system is going to have a bias towards things that look like cats, right, or cat features, right? So the specific body curve of a cat, or specific eyes of a cat, or specific pointy ears, or the longer tail, and so on. So that's okay. What's not okay is to build a system that does facial recognition and does so much better with recognizing, say, Asian people as compared to white people or compared to to black people. And really what it means is that you build your system, you trained it, you got your accuracy measure, it's technically correct. But then really what the same way you need to measure your overall system, you need to measure it for subset of a population, right? And especially if you're subset of a population that you are legally required or just morally the right thing to do, make sure you actually treat them correctly. Just make sure you measure them separately, right? And make sure that you actually have enough data points to measure them, right? And that's another mistake sometimes people do. So let's say I really want to measure the over age 75 population, but if you only have 25 people per week, you're not going to get any a measurement that's useful or statistically reliable in any sense. But I would say just start with the measurements. The other thing really just understand the system degrade, right? And sometimes people don't expect this because they still think software engineering, right? So to go to the example, look, if I build a calculator app, like, of course, that a year later it can still add and subtract numbers, right? Like it's not degrading, okay? But if you think about it, if let's say I have a clothing store, okay, and people come in and I'm showing my retail team in the store, look, here's what you recommend to people, here's how we merchandise, right? So here are the things that we put on top for everyone to see and go to the store. Here are the sales we have. If you don't change that, then your sales are going to go down, right? Because you start in the summer and now it's the middle of the winter and you still recommend your summer clothes, right? Because and that's really what happens. The world changes, the population you're serving changes, preferences of people change, which really means that if you have a system that really needs to learn from the environment, needs to actually do that once you're in production.
Yeah, I find that interesting, and we do often hear in the news about gender and racial bias with AI. Can you go over some other potential bias that people might not be thinking of?
Yes. So
I would think would
yes.
language be a potential bias?
So there are two things to be careful about. One thing to be careful about is definitely basically where you work as a data scientist, and basically just by not paying attention to it, you underrepresent some of the populations that your system is supposed to serve. So if I train my system all on American white people because I had a data set of 150,000 images from yearbooks and college books, okay, and I just happened to a nice clean data set of all the images in the same resolution and same format, and I had all the metadata goes with it and I trained it. That's nice, but then I need to know that it only works for that population. Okay, this happens a lot. Like in healthcare, you see this all the time. People get a huge data set from from one of the hospitals, and we've done, for example, we had several very large claims data sets a while back, and we could look at diseases that are long running. Okay, so things like kidney disease and diabetes and heart failure and so on. But then, for example, in healthcare, if you work with a hospital that, for example, does not take Medicare, you're missing the whole 65 plus old people. Oftentimes you just need to look at your data, at your training data, and just be very honest about what population it is representing, what population it is not, and know that your system is going to be limited to that. So that's one kind of bias, and really a lot of it is really, look, just pay attention to your own input data, right? Because often it's very, it's very easy to say, look, if you have a data set with 90% women and 10% men, you're going to, you are going to underrepresent men, right? Because that's no distribution that we have in the real world. So that's one thing. Another thing to pay close attention to, and other types of biases, is really systems that learn from junk or learn from signals that you did not intend for it to learn from. And that's not necessarily about bias, but really technically it looks at the same kind of problem. So one example in the paper about Lime, which is one of the algorithms to actually show explainability of supervised machine learning algorithms. And that's a paper from University of Washington. One of the nice examples you give is that they built an algorithm to basically classify different types of dogs. Okay, and basically I'm saying, okay, is this a husky or is this a wolf? Okay, basically, well, a wolf is not technically kind of dog, but let's say, right? And they look at a set of images, and then they build their explainable algorithm, which showed basically which parts of the images, and actually they're the well-performing classifier. But then the explainer algorithm showed where in the image were basically the differentiating pixels or aspects that told the algorithm to say, okay, this is a husky or this is a wolf. And then what the explainer algorithm shows very clearly is that the classifier learned to identify snow, right? So basically, if there was snow in the picture, it said it was a husky. If there was no snow, it said it was a wolf, which from their training set worked beautifully, right? Because mostly you see huskies on most images you see huskies on the background of snow. So that's one example where, okay, yes, you have an algorithm that actually performs very well in terms of accuracy, but instead, like, it learned the wrong thing, right? Because if you look at really what you wanted to know, it's like, look, if I'll show you now a picture of husky, other than the fact that I took all my training data from snow, from nature and snow-related pictures, you will never know what the actual difference is. I've had similar examples a while back when building machine learning algorithms to classify products into a category tree. So basically, you have an e-commerce website, and you have products, and you want to automatically classify them into the browse tree, right? So categories like consumer electronics, food, jewelry, and so on. Well, sometimes what would happen is there will be one brand name on one product line name, or even one style of writing a specific kind of spec. And the algorithm, because it was based on NLP features, basically learned that specific token, and then that token ties you back to a specific category. And basically, you look at it and you can say, yes, technically this is accurate in the sense that yes, this is what the training data tells you. But if you look at really, if you look at really what you need the algorithm to learn, in a sense that you've learned the wrong thing, right? Because you learn to measure training data, but what will happen in production is totally different. So I'd say that's, in a sense, that's a harder kind of bias to find out in practice. Because usually, look, if you're dealing with people and you're concerned about underrepresenting some different groups, so just look in your input data and see what's there. Okay, so I mean, healthcare, I can tell you, look, if you have a set of people and all of them are middle-aged women, then okay, build a model for middle-aged women. Don't tell everyone that this works for elderly people or it works for young kids, because it won't. But some of those biases that are really part of how the algorithm learns features are harder to uncover. And really, you need to what people need to learn to do is really debug their models to see that they're not falling really into those issues or bugs.
That's great. And so I wanted to get into just a few more of the audience questions, and just to remind the live audience, if you want to submit your questions, I will toss them up to David to answer. But we have one here that a lot of people are asking today, and I'll add on to it, but they're asking if you could explain in your words, what's the difference between machine learning and artificial intelligence? And I'll just add on to that, do you find that there's a mislabeling of both or either in the news by marketing teams or companies out there?
Yes, look, first of all, say yes. Look, there's a huge amount of hype and there's a huge amount of noise. which leads to a huge amount of confusion. Because machine learning was the hottest keyword you could tag on to a couple of years ago, and then everybody was doing machine learning, and specifically this year it's AI, so everybody is saying they're doing an AI, because so marketing incentives and financial incentives to do it, people move to specific words regardless of what they actually technically mean. I would say overall, it's not, I don't think it's good for the market overall, because part of the problem with any early stage market is that you need to actually educate people and reach agreement on what those terms mean. And really it means that people who are buying those technologies or trying to build them actually get more confused. Because they, if you talk to different companies or different vendors, they will just tell you conflicting things. Because that happens to be the marketing pitch, or really there's just disagreement in the industry about what they are. But that's in a sense, that's just the way it is in any early stage market, and people need to be aware of that. So a lot of the people who explain the difference between machine learning, deep learning, and AI, a lot of it is really, okay, look, here's my marketing pitch, which I need for my specific incentive, and that's that. I would say, look, in general, if you look at it from the academic computer science perspective, so artificial intelligence is sort of a bunch of computer science that's been around since computer science has been around really, since the 40s and 30s, if you want to go that far, with the eventual goal of trying to build artificial systems that would be as intelligent as people or better, as really as a scientific pursuit. And that means many things. That means some algorithms that really machine learning algorithms that learn as they go, and obviously learning is a key fundamental part of being intelligent. But then it also means algorithms that can do planning, or algorithms that can do search, or algorithms that can do many things. And of course we are obviously not at the point where we have in a sense like strong AIs or real AIs walking among us. But there are many things that we've been able to achieve. If you look at Google, so Google would easily in the 70s or 80s would be considered today a prime example of AI, in the sense that yes, you ask it question, it gives you a result that you want of this huge huge database of the world's knowledge. Same thing with recommenders, with image recognition, with financial system recommendation for detection. So there's a lot that's actually happened. But AI in general, computer science is the overall field. Machine learning is a subfield of that. Where people really are just concerned with really just machine learning algorithms, theory of machine learning, how you actually build systems that learn over time. So if you look at it as an algorithmic problem, it's different than classic algorithms. So classic algorithms, look, you give me input, there is a correct output, right? So let's say I need to sort an array of numbers. So I give you the numbers, you need to give me the sorted, and there is a correct solution, and that's it, and just give me an algorithm that does it all the time. In machine learning, basically, the problem is different, right? So the problem, I give you pictures of dogs and cats, right? I don't need an algorithm that differentiates them. I need you to train an algorithm from scratch. Basically, to train a model that can differentiate between them, and the algorithm that trains better as I show it more examples. So we managed to define the algorithm problem differently. You have different techniques that do it. So there's machine learning, sort of the subspecialty in computer science that deals with that.
Well put. So I wanted to ask a few more questions before we wrap up here.
Sure.
Just following up on that one. Do you? I understand that we're in a hyper growth stage of AI and machine learning now. Do you expect that to continue in the near future? And do you expect more and more industries to adopt these practices, or do you see a plateau coming up?
No, I think we are just getting started. I think AI today, it's a bit like the internet in 1995 or personal computers in 1978. Where I think right now, I think we're just getting started. We have easily a decade or two of really incremental progress. I think what we see today, there's a lot of excitement. There's a lot of work and a lot of people and a lot of money are going through these phases. But the reality is that the tools are clunky. We are improving the algorithms really by demand. There's a whole lot of education that needs to be done so that people actually know what they're getting, what works, what doesn't. There's a whole lot of noise in the market, and even academic research needs to be clarified. So I think we have a long and exciting road ahead of us.
And then finally, just along those lines, do you see government regulations coming into play soon, or do you see AI and machine learning, deep learning falling into current regulations, or will there need to be new ones?
So that's it's a loaded question, and many people have different opinions. So from what I see, I think it's way too early for any government regulation, because I think right now that there's still a lot of things we need to learn and understand about really how the technology works, what's doable, what does it actually impact, and I think if there are things we still need to figure out, as a community just building these technologies. I think right now, there's far more education and far more experience that we need to gather before policymakers and politicians can actually chime in and do things that are going to be valuable and successful. And I just think it's just way too early to understand right now what's going to be useful and even what's going to be important. And if you look at any other industry, if you look at the electricity industry, if you look at the car industry, radio industry, so all of the industries that today are regulated, they needed their first 20, 30, 40 years before those before useful regulations could come into play. Because I think right now really like the early part of every revolution, I think a lot of the companies and a lot of the players and a lot of the problems that we think we have today will just not exist in 10 or 20 years. I think there are going to be other problems that right now we're neglecting, or we think they're going to be marginal, that are actually going to be the biggest one. And even if you look at just the evolution of the internet over the past 20 years, you can see that, right? So if you look at something like social media, if you were to regulate the internet in 1995, that not only did it not exist, it was 15 years away, right, from actually being something that's relevant. And I was saying how you need to regulate it, probably 2 or 3 decades earlier. So I think, I think it's very early. What I would say is definitely right now as a practitioner, so I see it within myself, within my teams, there are definitely some questions that are, I'd say, moral questions and legal, and ethical questions that we hit, that are non-technical questions that need to be solved. Right now, I would say in most, I would say pretty much in every company I've worked in, we needed the R&D team to address them, because it was even very hard to even explain to others what exactly are the trade-offs that we're thinking about. So I think really like every technology at the beginning, right now we need right people to do the right things. But then I think it will take a long time before regulation will come into play.
All right, that was fantastic, David. I want to thank you for taking your time to do this Ask the Expert session.
Thank you very much. Yes, it's been a pleasure, and thank you for hosting.
Awesome. And just to the audience, if you guys want to catch the next session on cybercrime, you can find it in the attachments, and we look forward to seeing you there. Thanks, David.
Thank you very much.